Hey guys! If you're watching this, it's because we went backwards in time and we're going back to the board because my stupid dongle from my tablet is not working for some reason. But if you're not seeing this, that means I got it working. This is over the last 4 sections of our notes, 6.6 through 6.9. It sounds like a lot, but it's not really. It's the 4 ways to calculate enthalpy. And it shows you right here. Calorimetry, that's using the enthalpies of different substances within a reaction. Bond enthalpies, how much energy is stored within a bond. Enthalpies of formation, a table or a chart that gives you the amount of standard enthalpies for a particular substance. And lastly, Hess's law, where we talked about this a little bit earlier in the year, where you take a reaction, depending upon if it's flipped or multiplied, you do the same steps accordingly. And we'll get to all 4 of these examples by the end of this video. First up, it's important to understand that delta H is not heat. Delta H is measured in joules per mole or kilojoules per mole. It's not just heat. So don't get those 2 things confused. So delta H is the amount of heat given per mole. Of a product. So how much heat is given off per mole of that product. So to find this, you have to have moles, you have to have heat. Put them all together, you get heat per mole. The first type we're going to look at is calorimetry. That's a great example of a type of calorimetry device to measure it with right there. You've got a thermometer, a stir, 2 fuses, a bomb calorimeter, and then whatever your sample is. If it's aluminum, magnesium, barium, it'll give you that information based upon that constant volume bomb calorimeter. We don't have those to use in here. So for our lab on Monday, we're going to be using styrofoam cups. A lot more user-friendly. The one thing you have to understand though when we're using the styrofoam cups, we have to have constant pressure. Because as we know from Gay-Lussac's law, if you increase the pressure, you increase the temperature, which will then throw off your results of your calorimeter device. So you have to have a solution. Obviously, we're using solutions in these styrofoam cups. You're measuring the heat given off per mole of those particular substances. Real quick, a review of the first law of thermodynamics. All the energy in the universe is constant. You can't create nor destroy it. However, you can transfer it to other things. The heat lost must be equal to the heat gained by the surroundings and vice versa. So you do this by measuring the heat gained or lost by the surroundings first. And then compare that to measuring the temperature changes in solution. And then based on that information, you can solve for Q. And then once you have Q, you take Q divided by moles to get your kilojoules per mole. Using this formula. Right there. So, delta H of the reaction equals the Q of the reaction, or the heat, divided by the moles of the reaction. Let's do an example problem right here. First up, it wants to know the enthalpy change for a reaction if 0.158 grams of magnesium metal is combined with enough HCl to make 100 mils of a solution inside a coffee cup calorimeter. The HCl is sufficiently concentrated so that all the Mg reacts, The temperature of the solution rises from 25.6 to 32.8 degrees Celsius as a result. Find delta H in kilojoules per mole for the reaction written. We want to use 1 gram per mil as the density of this substance. That's the density of water. And 4.184 joules per gram degree Celsius for the specific heat. That's the specific heat of water. First up, we got to get Q using MCAT. So Q, or let's not do that one. I like big Q, equals MC delta T. Q is already isolated. So to find Q, we take the mass of the total, not just the magnesium, and it's 1 gram per milliliter, and we have 100 milliliters, so 100 grams. MC, 4.184, and delta T, our final temp is 32.8, minus our initial, which is 25.6, and that should give us our Q. Let's see what we get. 100 times 4.184 times 32.8 minus 25.6. And we're going to keep nearest whole number, which is 3,012 joules. Or, if we were putting that in kilojoules, we'd say 3.01 kilojoules. And that's negative because it's an exothermic reaction. Heat's produced. Remember, you have to think backwards on that. So that's the Q of the reaction. Now we have to find how many moles of that substance is there. Magnesium. First, take the mass. This is a simple little stoichiometry problem. 158 grams of magnesium. Got to have that one. 1 mole of magnesium. I forgot how many. What, 24 something. 24.30 grams of magnesium. And then we want moles of magnesium per reaction. We look at its coefficient. There is no coefficient, so 1 mole of magnesium for every 1 mole of the reaction. Now we got moles of magnesium cancel, grams of magnesium cancel, multiply straight across, we get 0.158 divided by 24.3. I can't do that in my head. Let's see. 0.158 divided by 24.3. A gross number, 0.00650. Moles. Our formula says Q of the reaction divided by moles of the reaction. So we're going to take 3.01 kilojoules divided by that number we just got. So 3.01 divided by 0.00650, and that gives us right at about negative 463, oh, that should have been a negative, kilojoules per mole for that reaction. Pretty simple. Use your specific heat formula and then do some stoich to find your answer. Let's do one more before we move to the second type of calorimetry or enthalpy change. This one says it's all about liquids. A student mixes 50 mils of 1.0 molar and 50 mils of 1.0 molar, both of these being HCl and sodium hydroxide, inside a coffee cup calorimeter. I can't say that word very well. The temperature of the resultant solution increases from 21 to 27.5 degrees Celsius. Calculate the enthalpy change for this reaction in kilojoules per mole of HCl. Assuming that the calorimeter loses only negligible amount of heat, we're going to assume that's 0. And the total volume of the solution is 100 mils, 50 from here, 50 from here. Again, the density is 1 gram, just like water. The specific heat's 4.18, just like water. So let's calculate Q first. We got 100 mils. It tells us each mil is 1 gram, so our starting mass is 100 grams again. Times 4.184. Now, you can put final minus initial, or on this one, it's so easy. 27.5 minus 21, 6.5. But if you feel more comfortable putting this, do it that way as well. Now, let's see what we get for that. 100 times 4.184 times 6.5, 2,719.6. joules, or if we want to put it in kilojoules, move that decimal 1, 2, 3 spots, we get 2.7 kilojoules. All right, and again, we increased our temperature. That's an exothermic reaction. That's going to be negative. Now, flip to the other side. We're only looking at HCl. So we take HCl's mass, which was 50, 1 gram per milliliter again. So that's 50 grams is our starting mass for HCl. And we're gonna use milliliters though, so we'll put our little divider here. 50 milliliters. Milliliters doesn't do us any good in Stoic. We gotta change it to liters. So 50 mils, 1,000 mils in every liter. 1 molar. That tells us there's 1 mole for every liter of solution. So we're gonna put that as our next step. 1 liter of solution is 1 mole HCl. These are pretty easy numbers. Mils cancels out, so does liters. 50 times 1 is 50. Divided by 1,000 times 1 times 1. And we plug that in the calculator. 50 divided by 1,000 is 0.05. 0.05 moles of HCl. And then last but not least, take your kilojoules, negative 2.7. Divided by your moles. Negative 2.7 divided by 0.05. And we get about negative 54 kilojoules per mole. All right, that's enough of technique number 1. Use your specific heat formula, get your Q, find your moles, take 1 divided by the other. It's not that bad, not that difficult. Let's see. having to erase things is so 20th century. This is just asking some basic questions. It says the equipment above is shown, it's provided so a student can determine the molar heat of solution for calcium chloride. Knowing the specific heat of the solution is 4.18, list the specific measurements that are required to be made during this experiment. So we got to have initial temperature, final temperature. So T, I, T, F. What else do we have to have? The mass of CaCl2 and the mass of H2O. That should be it. Initial, final, mass. All right. Is the dissolving process endo or exothermic? Justify using only the data. Initial temperature, 20. Final temperature, 36.5. Increased means exothermic. Because initial temperature, or I should say because final temperature greater than initial temperature. Okay, so there must have been some kind of energy released. Calculate the mass of the solution used. Let's see, what does it tell us? The mass of the calorimeter, water, and salt. So that's total mass. 61.54 grams. And then the mass of the calorimeter is 11.31, so to find the solution, it would be just subtract those two. 61.54 minus 11.31, 50.23 grams. All right, that's the mass of our solution. Determine the change in temperature. Again, final minus initial. 36.5 minus 20. We probably don't even need a calculator for this one. 16.5 degrees Celsius. Okay. The next part, calculate the mass of the solution. Oh wait, we already found that, sorry. Calculate the moles of CaCl2. All right. It tells us the molar mass of CaCl2 is 110.98. So to get the grams of CaCl2, based on those numbers it gives us, it says that 61.54 is the calorimeter, water, and salt, and then the calorimeter and water is 56.57. So subtract those two. 61.54 minus 56.57 equals, what does that come out to? .97 grams CaCl2. Now to get moles, we got to go way back to first year stoichiometry, gram to mole conversion. It gives us the molar mass. We don't even have to calculate it. So 4.97 grams of CaCl2 over 1 grams on the bottom. That's not how you write 110.96 0.98 grams of CaCl2 for 1 mole of CaCl2. Cancel those out, multiply straight across, 4.97 divided by 110.98. And let's see what that gives us. Uh, 0.0448 moles. 0.0448 moles. CaCl2. Now to get the molar heat of the solution, we're going to need those moles, and we're going to need the Q for the reaction. So to get Q, MC delta T, mass, it says was 4.97, right? Is that what we got? And then it wants the total of the solution, which is 50.23. Times 4.18 times the change in temperature, which was 61.54, no, 36.5, minus 20, right? We've already found these from the previous steps. And then we're going to multiply all of that together. 50.23 times 4.184. Let's see. Or it just says 4.18, so we'll just use 4.18. You never saw that. Times 16.5. Negative 3464. That's Q. We've already got moles. We just plug in that for negative 3464 divided by our moles, 0.0448. You get a really large number, negative 77,321. Or if they said kilojoules, we would say, let's see, what, or was that in joules? Yeah, that was joules per mole. Joules per mole. Or we could say 77.3 kilojoules per mole. Depends on what the question's asking us. All right, so let's wrap that one up. Let's move on to part 2. I'm not going to go over the stoic right here because it's pretty self-explanatory. I don't want to waste our time on that. This reaction shows the amount of heat energy required for the reaction as it is written. One mole of each reactant to form 2 moles of the product. So 1 forms 2. The second way we're going to look at delta H is through bond enthalpy. Bond enthalpy tells us that there's bonds that are broken and there's bonds that are formed. Breaking bonds forming bonds. Breaking bonds always requires energy, and forming bonds releases energy. So it gives you a little picture example over here. One molecule plus two molecules looks like oxygen. This is a combustion reaction. And this is methane. Bonds are broken, bonds are formed. You end up with less energy afterwards. That's an exothermic reaction. There's our delta H, the amount of energy from here to here based upon those bonds that are formed compared to the bonds that we had originally that were broken. The way you get this is by adding up the bond energies. For all the broken bonds and all the formed bonds. Because some are going to be negative, some are going to be positive. You add them all up, you figure out your bond enthalpy. Now, this is something you'll never have to memorize. You'll be given one of these tables that shows you what each type of bond, how much energy it has, how much it releases, or how much it takes to form that bond. So you'll be given a table. You won't ever have to memorize this kind of stuff. Bond enthalpy is the energy to break a bond. Based upon breaking a bond is an endothermic reaction. So if you have an endothermic reaction, the bond enthalpy is going to be positive. And then on the other side, bonds that are broken in the reactants and formed in the products you can use the following equations to calculate the delta H for bond enthalpies. Now, key point right here. You're going to need this for the test. Maybe my test, for sure the AP test. Delta H of the reaction equals that big goofy looking E, that's the sum, or sigma. Sum of the bonds broken in the reactants minus the sum of the bonds formed in the products. You got to just know that. So delta H, when you're looking at bonds broken, bond enthalpy, sum of the bonds broken in the reactants minus sum of the bonds formed in the products. Commit that to memory. Let's do an example of this. Let's see here. Let me scroll up where it's easier to see. Hydrogen gas, a potential fuel, can be made from the reaction of methane and steam. Use bond enthalpies to calculate delta H for this reaction. All right, so first up, we got 1 methane plus 2 waters, or 2 steams, yields 4 hydrogen and 1 carbon dioxide. So I'm going to draw this out real quick. We've got carbon in the center. We got 1 of him. We got 2 H2Os. Yields 4 H2s. We'll just put thing, give myself enough space. Plus CO2. Now, we're going to flip back to that page real quick. What is a carbon to hydrogen bond worth? 413. So I'm going to say there's 4 of those bonds. So 4 times 413. What about oxygen to hydrogen? Where is it? Right here, 467. And there's 4 of those as well. So 1, 2, 3, 4. 4 times, I've already forgot, 467. And then the next part is hydrogen to hydrogen, which is 432. There's 4 of those as well. Again, we're just counting bonds. We're not counting atoms or molecules. Just the bonds. 432. And lastly, we have a double bond, oxygen to carbon. So we're going to look down here. 745, it looks like. Let's see. Is that double? No, what is that? Oh, 799 in CO2. That's where we're looking at. So, and there's 2 bonds. So 2 times 799. All right, now we've got all of our numbers. We can go back and get this thing out of our. There we go. So first up, we're going to start by calculating all of these totals. 4 times 413, 1652. 4 times 467, 1868. 4 times 432, 1728. All right, and 2 times 799, 1598. All right, let's see if I got that right. 15, 16, yeah. So we're going to add these two together. 1652 plus 1868, 3520 kilojoules per mole. For our reactants, add our 2 products up. 1728 plus 1598, 3326 kilojoules per mole. What was that again? 3326. Okay. I got a great memory, I promise. And then bonds broken in, or bonds formed in the products minus are subtracted from our bonds in the reactant. So 3520 subtracts 3326. And let's see what we get. 194 kilojoules per mole. So reactants minus products, total energy gives us 194. It's positive. That tells us this is an endothermic reaction. All right, should we do one more? Maybe. Let's scroll down to number 3. Let's see. The decomposition of ammonia. we've got 2 molecules of NH3. So let's say NH, why am I drawing atoms instead of the letters? And technically NH3 has unshared pairs, but we're not worried about that. We're only worried about the bonds. And we got 2 nitrogens, so nitrogen's a triple bond to itself, plus 6 hydrogens. There we go. Now we're going to scroll back up to that. No, get off of there. All right, over here we got 3 nitrogen to hydrogens for each. So let's find nitrogen to hydrogen. 391. And that's 6. 3 and 6. So 6. 391. We have 2 triple bonded nitrogens. So let's find that down here, right here. No, that's double. Triple bonds, 945. So 2, 945. And then lastly, we've got 6 hydrogen to hydrogen, which was 432. All right. Now we got that information. We can go back down to our problem. 6 times 391. 2346. Cancels. That's here. 2 times 945. 1890. And 6 times 432. 2592. And we're going to add those 2 together. Plus 1890. It's 4482. Reactants, total energy minus products total energy. $23.46 minus $44.82. Negative 2136 kilojoules per mole of the reaction. Negative number tells us that the exothermic reaction, so it's releasing the energy into the atmosphere. All right, 2 down, 2 to go. Standard enthalpy. Standard enthalpy of formation, known as delta H sub F, also known as heat of formation, is the change of energy that takes place when 1 mole of a compound is formed from its component pure elements in their standard states. From its component pure elements in their standard states. All right, that was a lot. But say it's things like graphite. You add up all the individual particles, all the individual parts, you get the standard enthalpy of formation for graphite. Once you have an enthalpy of formation, the particular product is more stable than its constituent elements. The standard enthalpy of formation for a pure element, meaning one element by itself, unchanged by anything, in its standard state is 0. You just have to know that. Memorize that. Make that a key point. So like calcium, bromine, doesn't matter. Standard state, 0 kilojoules per mole. By themselves. When put together, then they can find or produce some sort of enthalpy. All right, let's move up a little bit. The degrees tells us that we are dealing with the standard state. So when you see that degrees of F, that tells you that we're dealing with the standard state, which specifies certain conditions. Standard state for any pure substance is defined according to the following. The pressure has to be at 1 atm. For solids and liquids, the standard state is the most common stable form. At 1 atm, again, standard pressure, and 25 degrees Celsius or standard temperature. Br2 liquid is the standard state of bromine. Bromine is one of 2 elements that's standard state is liquid, mercury being the other one. Carbon standard state is in graphite, and it's a solid, not diamond, or else we'd all be millionaires. And then for solutions, the standard state is a concentration of 1 molar. Makes it easy, 1 mole per liter. And you're going to be given these values. You don't have to memorize this. I'll give them to you in the problem in a minute. All right. Delta H of the reaction equals the sum of the standard components of the products minus the sum of the standard components of the reactants. So to calculate delta H of the reaction, you subtract the enthalpies of formation of the reactants multiplied by their stoichiometry or stoichiometric coefficients. from the enthalpies of formation of the products multiplied by their stoichiometry or stoichiometric coefficients. And again, pure elements, 0. Don't have to worry about those. All right, let's do a couple of these and we're going to move to the last example. Let's see. Use the standard enthalpies of formation to determine delta H for the reaction. This is NH3 plus oxygen yields nitrogen monoxide and water. First up, delta H. The formation equals, and I cannot draw these things. Something like that. Give me a break. Sum of delta F of the reactants, or products minus the reactants, I should say. So in this case, and you'll be given these. Look at the products first. We've got 4 molecules of nitrogen monoxide. Nitrogen monoxide's standard enthalpy is 90.4. And then we need H2Os. Let's see. Negative 241.8. And there's 6 of those. All right. And now we're going to go to the reactant side. First up, we got NH3, and that is a negative 46.2. Negative 46.2. There's 4 of those. Plus 5 oxygens. How many is that going to be? We'll write it just so that you're not confused, but it's a pretty easy math calculation. 5 times 0. All right, let's cancel that out first off. 4 times 46.2. 184.8. Okay, now over here we actually have to do a little bit of math. 4 times 90.4, 361.6. And let's see, 6 times negative 241.8. 1450.8. Negative. Add those together, plus 361.6. Negative 1089. Negative 1089.2 minus a little bit. So negative 1089.2 minus 184.8. Gives us 904.4, and that's negative. Kilojoules per mole. Exothermic reaction. Again, you'll be given these values. You just have to multiply it by their coefficients, add them up, and then take products minus reactants. We'll do one more. Let's look at the thermite question. In thermite reaction, which powdered aluminum reacts with iron oxide, it's highly exothermic. So right off the bat, we should get a negative number here. We got 2 aluminum plus iron, what is that? Iron 3 oxide yields aluminum 3 oxide, 2 oxide, plus iron by itself. So we're gonna go ahead and write 0 kilojoules, 0 kilojoules. And then our standard enthalpies for iron 3 oxide are negative 822.2. And for aluminum 2 oxide is negative 1669.8. And then delta H we're going to take products minus reactants, or negative 1669, times its coefficient, which is just 1, plus 0, minus our reactants, 2. Oh, yeah, this should have been 2 times 0. I gave it away, though. Plus 2 times 0. Because you got to multiply it by its coefficient, even when it's 0. Plus 1 times 822. This is a waste. This is a waste. So we get negative 1669.8 minus, now remember it's minus a negative 822.2. We get negative 847.6 kilojoules per mole of the reaction. I find this one to be one of the easiest. You're given the tables, you're given the values, you just have to multiply by the coefficients, add them up, and then don't forget products minus reactants. All right, last thing, Hess's law. Mrs. H has joined the party. Let's see, chemical reactions. Obviously, we can break these down into a series of smaller steps. Like so. We've showed this before. I think it's back in Unit 2, but we didn't get into delta H that much at that point. All we're going to do is simply add these up, or we're going to calculate it by the sum of the delta H values for all the steps. But we have to remember to multiply or reverse based upon the equation that they give us. If a chemical reaction or chemical equation is multiplied some factor, then you have to multiply the delta H by that factor as well. So delta H is also multiplied by the same factor. So for instance, you got A plus 2B yields C, that's delta H1. If you put a 2 in front of that, 2A plus 4B yields 2C, delta H is 2 times the original enthalpy. And then so forth. You keep adding things, you got a 3 here, 3 here, 3 here, delta H will be what? It'd be delta H1 times 3. In this case, it's a negative though. So let's write that. It would flip the sign to, let's see, positive 393.5. No, I forgot my kilojoules. Now that was if it's multiplied. If it's reversed, some of you may remember A plus 2B yields C. We flip the sign. So delta H of the reaction changes signs. So A plus 2B yields C. C yields A plus 2B. We take delta H1 and we put a negative in front of it. So like on that second example, if you look at it, delta H flips this sign, it'd be 393.5 kilojoules. I think I gave you the wrong value for this one, sorry. Negative 1180.5. Some of you are like, what the heck is wrong with this guy? So for example 1, it's negative 1180.5. Example 2 is positive 393.5. And then if you have multiple steps, you have to take the sum, getting tired of seeing that word, of the heats and the reaction steps. And this is known as Hess's Law. We briefly mentioned this in Unit 2, so it's not a whole lot of new stuff, but a little. So let's look at this example. You got step 1 is 181 kilojoules. Step 2, negative 131. To get your final, you just add the two together. So 181 plus negative 131, I can do mental math. 50 kilojoules. Oh, here's a quick reminder. What is this thing called? When it's formed in one step and then used as a reactant in the next? Intermediate, and they're not included in our final reaction. You can see it over here too. The two nitrogen monoxides do not appear in the final. N2, two O2s produces two NO2s. All right, we'll do a couple of reactions, examples, and then we'll call this a day. So it says find delta H of the reaction for this reaction. And it gives us 3 steps on the right-hand side. First up, number your steps. If they're not numbered. 1, 2, 3. It's kind of hard to see, but you have your notes in front of you, so it'll help. Let's see, we've got 3 carbon plus 4 hydrogen yields C3H8. When we look at the first equation, the C3H8 is on the wrong side. Now, there's no carbon or hydrogen in that step, but C3H8 is on the wrong side. So we're going to reverse number 1. And it was negative 2043. That makes it positive 2043 kilojoules. Step number 2, we've got 3 C's, 4 H2s. Over here we got a carbon, no H2s, no C3H8s. It's on the reactant side, but it's triple the value up here. So we're going to multiply this by 3. So multiply number 3 by 3. Its original value was negative 393, which gives us negative 1180.5. And then the last one, 2 H2s plus O2 yields 2 H2Os. All we have is H2. We got 4 in our final. It gives us 2 in that step. So we're going to multiply number, I wrote 3 here. Multiply number 3 times 2. And that gives us, let's see, negative 483.6 times 2 is negative 967.2. Now you've got the 3 equations, how they were manipulated, and then you've got the values that correspond to that manipulation, and you just add them all together. So 2043, in this case, plus negative 1180.5, plus, again, a negative 967.2, and it gives us negative 104.7. Kilojoules per mole of the reaction. One more. Let's look and see which one we want to do, 2 or 3. We'll do number 2. Oh look, my numbers kind of match up. So we'll leave them there. NH3 plus O2 yields NO plus H2O. You got 3 steps. Step number 1. What matches up? Let's see. We've got NO on the product side, but it's twice, right? Because we had 2 there, there's 4 here. So we're going to multiply number 1 by 2. ones was 180.6. Multiply that together, you get 361.2. And then let's see, what about number 2? NH3s on the product side. N2 and H2 aren't part of it. So we reversed. But we also noticed that NH3 went up from 2 to 4. So we're going to do both. Reverse number 2 and multiply by times 2. So what does that give us? Negative 91.8, negative 91.8 times 2, and then we're going to reverse that sign, 183.6. And then lastly, 3, we got O2 and 2 H2Os. So 2 H2Os turn into 6. We're going to multiply number 3 times 3. And number 3's value is negative 483.6 times 3. Negative, no, I'm looking at the wrong value, sorry. Yeah, negative. There's a typo. Times 3. Yeah, definitely a typo. I'm getting negative 1450 times 0.8. That's why I do this math too and not just look at the notes. Negative 1450.8. And then add these up. 183.6 plus 361.2. Negative 906 kilojoules per mole of the reaction. So my notes have the correct answer, they just have the wrong value right here. Text me on Remind if you have any questions. Otherwise, show up next time ready to make some hand warmers.